And then now second one option that is we are going to work is the laminar flow between two parallel plates. And I want to discuss one thing here, that is right now what we are doing here is that we are going to place the axis system over here. Okay, so y is here and x is here. This is 2D case, and third dimension is the width that we are taking as a 1 unit. So xy is here, and here the y is equal to 0, and here y is equal to height. Okay, so in some cases, some derivations you might have seen that they take the axis over here, and so here is a h, and also on the bottom side it's a h. In that case, I think you might have seen that this u is equal to 1.5 times u maximum and 1 minus y by h square. But what we are going to do is that we are going to do the things in a different way. So we are going to drive the equation in this way, where the y is 0 at the bottom plate and y is equal to h at the top plate. This is the flow between two parallel plates. And third case is the flow on the flat plate, but on the top side we have free surface or free stream. This is simple. Simply speaking, this is something similar to the flow over a flat plate. Okay, so now let's discuss about this thing here. Okay, so we are talking about the flow between two parallel plates. Okay, flow between two parallel plates. Okay, so here is the drawing for these two plates. Okay, so we are introducing the uniform flow at this location, and that's with the u mean or free stream velocity. And the velocity profile is going to be developed at some length, and that is going to be the parabolic type of the profile. And total height of the channel is h, and the axis system is such that we have the axis over here. So x is here and y is here. So here y is equal to 0, and on the top plate the y is equal to h. And similarly you can see, so let me draw this thing on the other side. Okay, so here y is equal to h, and here on the bottom plate y is equal to 0. And maximum velocity you can see is on the center plane. This is the u maximum. So the boundary conditions from the figure you can see, these boundary conditions are that at y is equal to 0, u is equal to 0. And at y is equal to h, again the u is 0, but at the y is equal to h by 2, u is equal to u maximum. And also at the y is equal to h by 2, the du by dy is equal to also 0. The gradient with respect to y is 0 here. Okay, so we continue with this thing, and now we take a small element on this geometry, and this small element is over here. So the dimensions of the element is, it's a 2D case, so this is the dx and the dy in the vertical direction, and the forces are the px, and here we have px plus dx, and here we have the tau xy, and direction is in this way, and the direction on the bottom side is in this way. Okay, again the force balance says that this px into area. So area would be the dy and minus px plus dp by dx into dx whole bracket into dy. This is the area normal to the surface. So why this is area? Because this is the 2D dimension is height is dy, third dimension is the 1, so this is like dy, and the 1 is in the third direction or in the z direction. So you can see the area of a rectangle is equal to 1 over dy or simply dy, and then minus shear stress into area. So area would be here would be equal to dx plus the shear stress that is in the y direction definitely or xy. So shear stress plus d by dy of shear stress, and so also the dy here into dx. Okay, so the area here is a dx is equal to 0. So we can cancel out the px dy and px dy. Similarly, shear stress into dx, shear stress into dx can be cancelled out very easily. So finally we have so I will simply write down the dp by dx and dx dy plus d by dy and the shear stress into dy into dx is equal to 0. So you can cancel out the term dx and dy throughout from the both sides. So now the equation says that we have this thing. So we have and this thing would be like a minus term. This term will be minus term and this term will be positive term. So we have so we can write down the d by dy and the shear stress is equal to, this will be on this side will be positive quantity, so dp by dx. And now we know that the shear stress is equal to mu du by dy. So we can insert this term and we can take out the mu from this side and we can take it on this side. This will be 1 upon mu. So let me change my pen. So we have the d by dy. So let me write down the complete term here. This is the mu du by dy is equal to dp by dx. So now from here we can write down that this is equal to the d2u by dy2 is equal to 1 upon mu dp by dx. Okay, so we have these terms in this way. And now if you take a look here, if we integrate this equation 2 times, so first time this will be du by dy is equal to 1 upon mu the dp by dx y plus c1. Again integrate, this will be the u is equal to 1 upon mu and the dp by dx y square upon 2 plus c1y plus c2. And the boundary conditions would be that we have boundary conditions would be that at y is equal to 0, u is equal to 0, and at y is equal to h by 2, the du by dy is equal to 0. So from this equation we can find out that the du by dy is equal to 0 at y is equal to y by 2. So I can write down that c1 is equal to minus 1 upon 2 mu and h can be on the numerator dp by dx. Okay, so we found out the value of c2. Okay, so c2 is this term minus 1 upon 2 mu and dp by dx and h is also numerator. And from second boundary condition, that is when the y is equal to 0 and u is equal to 0. So from this, the y is 0, u 0, so C2 is equal to 0. So second boundary condition will reveal us or give us C2 is equal to 0. So now I can write down the u is equal to 1 upon mu, the dp by dx, y square upon 2, and minus 1 upon 2 mu. So we can write down this thing as 1 upon 2 mu. 1 upon 2 mu, and so C1 is h. So dp by dx and hy. Okay, so let me write down this thing again. So u is equal to 1 upon 2 mu dp by dx, y square minus 1 upon 2 mu, and dp by dx hy. Okay, so from here we can take out common minus 1 upon 2 mu, minus 1 upon 2 mu, and dp by dx. So we have hy minus y square, hy minus y square. So now also we know that the u is maximum at center point. So u is maximum at center point where y is equal to h by 2. So for maximum velocity, we know that the u is maximum at y is equal to h by 2. So if I put this thing, so I can get the u maximum is equal to minus 1 upon 2 mu and dp by dx. So h by 2. So h into h by 2 minus, so we have the h square upon 2 square, 4. So 1 upon 2 minus 1 upon 4 is equal to 1 upon 4. So we have u maximum is equal to minus 1 upon 8 mu and dp by dx, and this is h square. So I can write down this thing as a minus h square upon 8 mu dp by dx. Okay, so this is also a u term. So if I write down this thing, this u as minus, if I take out the h square common, so this will be h square upon 2 mu from this equation, and dp by dx. So we have the y upon h. So we have the y upon h, and minus we have y square upon h square. Y square upon h square, this is the y upon h whole square. Okay, and if I write down this thing as so I can write down this equation in terms of u maximum as, so let me write down this u in the u maximum, then we will convert this into u mean. So I can take out the, because you know that u maximum is minus h square upon 8 mu. So I have to put here minus h square upon 8. So I have to multiply with 4. Okay, so dp by dx, and remaining things are exactly same. So y upon h minus y upon h whole square. Okay, so this term minus h square upon 8 mu dp by dx is equal to u maximum. So u maximum will be equal to, so this is u maximum. So we have the velocity profile u is equal to 4 times of u maximum into y upon h minus y upon h whole square. Okay, this is one form, but again, as I told you earlier, that u maximum is not a known quantity, so we have to find out the u this term in terms of u average, that is the velocity at the inlet. Okay, so for that we have to find out the value of, and also the u maximum is or was given by minus h square upon 8 mu and dp by dx. Okay, so now we have to find out the value of v average. So v average is in a similar way. So the u mean is equal to uh, 0 to h q dA and divided by area. So for the two-dimensional channel, the area A is equal to h, and the dA is equal to into 1, dA is equal to dy into 1. This is equal to h, this is equal to dy. Okay, so I can put the velocity profile here, and velocity profile I will be putting in terms of the h square. So this is 0 to h, and so I can write down the q as, so our q would be like is q, so this is the q into dA. Okay, so you know that if we multiply velocity with area, so we will be getting the flow rate. So the flow rate is now will be like this. So dA, so this is going to be the u into dA. Okay, so the integration of q will be equal to u into dA. So the u is minus h square upon 2 mu and dp by dx y upon h whole square and bracket close, and the dA is equal to, in the for small element this is equal to dy into 1, so dy, and divided by area in for the whole channel this is equal to h into 1, so h. Okay, so from here, okay, let me simplify this equation. So minus 1 upon h integration 0 to h minus h square. So the h square I can take inside the bracket. So this is minus 1 upon 2 mu and dp by dx. So if we take the h square into bracket, this will be equal to hy and minus y square into dy. So now integrate this whole equation. So we would be getting here 1 upon h so 1 upon h, and take this thing outside. This is equal to minus 1 upon 2 mu dp by dx. Integration will reveal us that this is equal to h y square upon 2 and minus y cube upon 3, and limits of integration are h and 0. So now we can simplify this thing, minus 1 upon 2 mu h and dp by dx, and this is equal to the, if we put the limit, this will be y square will be h square, so h cube upon 2 minus h cube upon 3. So this is equal to 1 upon 2 minus 1 upon 3 is equal to 1 upon 6. So this is equal to minus 1 upon 2 mu dp by dx, and this 1 upon h is here, 1 upon h and h cube upon 6. So h cancel, we have the h square here now. So this term is minus 1 upon 2 mu dp by dx and h square. So this is the term for the u mean. So u mean is equal to u mean is equal to 1 upon 2, and also we have the 6 here, so this will be equal to 12. So minus h square upon 12 mu dp by dx. And u maximum was equal to minus h square upon 8 mu and dp by dx. And we got the u in terms of also maximum. So this is the 4 times u maximum. So 4 times u maximum, and bracket start. This is a u function as a function of y. So this is the 4 times u maximum, and in the bracket we have the y upon h and minus y upon h whole square. So y upon h minus y upon h whole square. So now if I divide the u maximum with the u mean value, so I can find out this is equal to minus h square upon 8 mu dp by dx divided by minus h square upon 12 mu dp by dx. So after cancelling, this is equal to 3 by 2. So this is equal to 1.5. Now if I multiply this 3 by 2, if I put the u maximum is equal to, so u maximum will be equal to, u maximum is equal to 3 by 2 3 by 2 and u mean. Okay, so I can now write down the u as u is equal to 4 times 3 by 2 u mean into y by h minus y by h whole square. So we have this term as, so table of 2 is a 1 to the 2 and 2 to the 4. So this is equal to 6 u mean y upon h minus y upon h whole square, and u maximum upon u mean is equal to 3 by 2 for the channel. And similarly you can write down the equation for pipe, and this equation should be, in terms of u mean, this will be equal to, so in terms of u mean, this equation for the laminar flow in the pipe, this will be u is equal to 2 times u mean 1 minus r square upon r square. Okay, so in this video basically we learned that how to find out velocity profile for the flow between two parallel plates, and we set the coordinate system such that the bottom plate is on the y is equal to 0 and top plate is at the y is equal to h, and the center plane we have the velocity maximum, we have y is equal to h by 2. So now this is the whole step for derivation, and finally we achieved the velocity profile in terms of the u mean. Okay, so the u mean is 6 times u mean y by h minus y by h whole square. This is exactly same as shown here. So 6 u maximum, this is u mean. Okay, y upon h minus y upon h whole square, and u maximum is equal to 3 by 2 u mean. So this is the equal to 6 times of the u mean. And similarly here, okay, so basically we drive the second profile, and in the next video I will be driving the third profile.